I'm with Hertz Marketing. We're your new local manufacturers rep in your respective territories, and we're very happy to host today's presentation. We got a couple of house cleaning items here. We're gonna mute all the phones out of respect to the presenters, but we will have a question and answer session. After the presentation, you can do that verbally, or you can just do it through the chat feature at the bottom of the screen. And also, we will upload. This is going to be recorded, and we will upload it to our Megahertz website if you want to review it later or share it with someone else in your respective company. So without further ado, I'll turn it over to our presenters. That would be Vince Brocato. He's a senior sales director at SiTime, and Jim Holbrook, who is a applications engineer. So go ahead, gentlemen.
Thanks. I'm going to go ahead and present maybe a couple slides right up front, and then Jim's going to dive right into the training. Some of you may or may not know who SiTime is, so just wanted to give some highlights right up front. Jim, can you advance the slide, please?
So Vince, can you say what slide I've got it on slide 2 now.
Okay.
Is it showing?
Okay, there it is. There it is. Yeah, it just came up. Okay, so very high level. SiTime is a company that's dedicated to developing timing solutions. We are a pure play timing company, and we're a pure play MEMS timing company. We do not do Quartz-based solutions. A couple of high points here. The company did go public in November of 2019. We're traded on the NASDAQ under the symbol SITM, and the valuation of the company has done very well since then, gone up by a factor of 4. We have 90% of the MEMS timing market, but more importantly, we're the #2 shipper of all oscillators in the world. And you can see all the different markets that we support there. Go ahead, Jim. Our solution, the reason that we're gaining so much market share in the timing market is we continue to improve on the various parameters, important parameters for timing products, oscillators, and clock generators, and what have you. You can see some of the numbers there as far as improvement is concerned for frequency stability, jitter performance, Allen deviation, and size reduction. So we are siliconizing timing, and we're improving performance at the same time. Go ahead, Jim. And this is the last one. Our core technologies are certainly the silicon MEMS resonators. We developed our MEMS resonators, or fabricate our MEMS resonators in Germany at Bosch. The two founders of the company actually came from Bosch, where they developed the deep ion etching technology that Jim is going to talk about later on. We are on our 3rd generation of MEMS resonator. In addition, with all of our designs, we also have a mixed signal CMOS ASIC internally. These two devices, the resonator and the ASIC, are mounted in a stacked die formation, and in some cases encapsulated in plastic, and in other cases encapsulated in ceramic for high performance solutions. We use Taiwan Semiconductor for our CMOS technology. That's a 0.18 micron process technology, and the Bosch process is a 0.3 micron manufacturing process. We use standard semiconductor fabrication. Standard semiconductor packaging and test houses like ASE, Carsem, and UTAC. And I think with that, I'm going to turn the floor over to Jim, who will dive into, and we've got over 15,000 customers worldwide and over 200 applications. So with that, I'll turn it over to Jim.
Okay, thanks, Vince.
Sure.
So I normally just kick off with a couple of videos that kind of underscore the advantages of SiTime MEMS technology, and that's what I'm going to do here. So one of the big advantages that we have, and there's a little music with this, is our shock and vibration resistant. So I'll just kind of let it play because there's audio about to kick in.
Jim, you might have to turn that audio up.
Okay.
Hey, Jim, the audio didn't play. You might just want to explain briefly what they saw.
Oh, okay. Yeah, I'm not sure why the audio didn't come through. But what I'll do is I'll just kind of narrate it myself. And so basically, what we have is a custom test board that we did. This is a shock fixture. And we've got this PCB board and the shock fixture with basically our frequency measurement. So we can see how much the frequency changes with each strike. And so the next will come up is just a close-up of the board. So you can see the SiTime TCXO to the left, and this is actually a competitor OCXO. It's a Raycon Mercury class OCXO in 9x7 millimeter package. And this is the strike plate in the center, of course. And what we're doing is we're just basically hitting this strike plate, and then these frequency counters are projecting up the real-time frequency response of the Raycon OCXO versus the SiTime PCXO. And you can see basically there's no response of the MEMS to the strike. And the Quartz is having pretty large, up to 30 ppb frequency. Okay, so that's a quick video. So I'll just pause that, and then I've got one more video to demonstrate a different attribute. And so this basically shows the stability and airflow and fast thermal transients. So we have a similar type of test fixture here where we have a side-by-side comparison of of our board, and there's a close-up here. So this is an older version of our TCXO in plastic package that actually the latest ceramic is even better performance. This is a premium grade TCXO from Raycon. It's a RPT 7050, a Pluto class TCXO, which is considered a telecom infrastructure grade. And we're just going to do a side-by-side comparison through several stresses. So the first test, we're going to start mild, and the first thing we're going to do is just remove the plexiglass cover. And let me just explain the display a little bit so you can see what we're looking at. On the left is the 50 ppb Quartz TCXO, and this is the frequency deviation relative to time zero. And then this is the temperature of the board. We have an RTD on the board and we're measuring it real time. And then on the right is the SiTime MEMS Super TCXO, same thing, frequency relative to time zero, and basically the RTD near that device showing the temperature. And the other thing we have is the Allen deviation, which is just a measure of a short-term frequency stability. Lower numbers are better. And we'll see how things perform. So you can see just by removing the plexiglass cover, the Quartz is jumping around on the order of a few ppb, and you can see the commensurate increase in Allen deviation. Again, the lower numbers are better, and just removing that plexiglass cover, we see an order of magnitude difference in Allen deviation. And this is due to the better construction of the MEMS and also our superior temperature compensation. And we'll talk more about that later. But you can just how sensitive, and it also kind of underscores these minute temperature changes that occur just in a normal lab environment that you may not be aware of, but they do impact the quartz. And even though this is single-digit frequency excursions, for wired telecom applications with 20 ppm specs, this may not, be a big concern. But in RF type of applications where you have a reference oscillator to a frequency synthesizer, with a high frequency multiplication factor, this can actually impact the radio performance. So now we kind of have our baseline in a pretty benign environment. We just took off the plexiglass cover, so it's exposed to the small ambient airflow changes and associated temperature changes. And you can just see the scale difference between the two. So now here's where we start increasing the stress. So here we turn on the fan. You can see that the Quartz device jumps up to about 50, almost 60 parts per billion. And that's actually, now it's exceeding its datasheet spec. It's got a 50 part per billion datasheet specification for frequency stability. And by contrast, the MEMS is relatively speaking flatline. You're seeing a fraction of a ppb frequency changes, and the Allen deviation is still hanging in it on the scale of e to the minus 11th versus the Quartz, which is about 2 orders of magnitude, a little more than that, worse in terms of short-term frequency stability. And you can also see the board temperature changes through this process. So that was the first stress, and then we're about to get one level higher in terms of stress in just a second. So we'll turn off the fan momentarily, and we'll let the TCXO settle, the Quartz TCXO settle back down to what it was before, and we're basically done with that experiment. The next experiment is actually the most severe, and we have some other experiments as well, but I'm going to stop it after this next one because this is the most severe test. So in this case, we're going to hit the part with a heat gun, as you'll see momentarily. So here, plexiglass covers off, and then you'll see the heat gun come into the picture in just a second. So you can see with the heat gun, the Quartz is popping down to minus 450 part per billion, and it kind of overshoots, and then it's trying to basically overcorrect, kind of a whipsaw effect from minus 450 up to a little over plus 200. So the peak-to-peak deviation is actually about 650 ppb, and you can see now we're seeing single-digit ppb on the MEMS TCXO. Now the ADAV is on the order of e to the minus 10th, so it is seeing it, but it's controlling the frequency to 2 orders of magnitude better in terms of controlling the short-term frequency stability versus Quartz in terms of ADAV. And then you can see just the output frequency, the huge difference, 1.63 ppb versus at this point we're now at 172 on the Quartz device. So that really underscores the robustness of the MEMS in real world type of conditions. And, it's true that people aren't going to be applying heat guns in the real world. But what this does kind of emulate is the oscillator sitting next to, in close proximity to an ASIC that may be high power and it's coming out of a sleep state. So in those type of situations where you're next to a high power ASIC or FPGA that's coming in and out of sleep states, you can get these very fast thermal transients that can affect the device, and you can see the difference between the two. So that concludes the videos, and so the reason I show these videos up front is to to give you some motivation as to why you might care about MEMS versus Quartz. Quartz has been around in its present mass production form since World War II, and even before that, as we'll talk about, in kind of handcraft custom for radios since the 1920s. And MEMS is coming into its own in the mid 2000s, and I think it demonstrates some some really tangible values to real world systems. And this is to kind of motivate really why you should care about MEMS. And we'll get more into some of the construction that confers these beneficial attributes later. But we'll start very, very basic just to kind of level set some terms and talk about what is a clock and move on into crystals and resonators. And then we'll jump into the MEMS construction and some of the reasons that MEMS is superior in many different attributes to quartz. So in simplest terms, a clock uses some resonance. Usually it's a mechanical resonance. So you get a periodic frequency, and then you have an integrator to integrate that frequency into time. And brief history, really the first pendulum clock, again demonstrating mechanical resonance, was in 1656. And then you had the spiral balance clock about 20 years after that. And then kind of the big technology leap was a quartz crystal based resonator that's used for a clock that came into being in 1927. And then the next big leap was in the late 40s for the atomic clock. And now MEMS came into its own in terms of a clocking source really in the mid 2000s, 2005, 2006. When SiTime, as well as several other companies, launched their MEMS products into the market. And then you can basically take this mechanical resonator and you can add additional features such as temperature compensation. You can ovenize it and so forth to get even better stability. And of course, the ultimate stability is the atomic clock. Usually either cesium beam or rubidium based atomic clocks. So what is an oscillator? So an oscillator is really, you take a resonator, and the resonator, if you think about it, is really just a very narrow bandpass filter. And you bolt up that resonator, which is essentially a bandpass filter with a very narrow pass band, up to an amplifier. And so during startup, the amplifier is generating kind of broadband noise. And this resonator is the frequency selection element because it will filter everything out of this narrow pass band and pass through basically it's the frequency that is the resonant frequency of the device. And so as you first start up, you inject this broadband noise, the frequency that corresponds to the resonant frequency of the filter gets through, gets amplified again, and basically you build up to an oscillator, a stable oscillation. And the amplitude grows until it's limited by the amplifier power supply or regulator, if there's a regulator. And you get a stable frequency. And of course, you know, the well-known criteria for oscillation is gain around the loop greater than or equal to 1, and phase shift 0 degrees or multiples of 360. So you get the positive feedback effect to maintain the oscillation. So that's the basic of oscillators. So now we'll talk about resonator versus oscillator. Again, we're kind of starting very basic. This is well understood by pretty much everyone, but just to kind of level set terms and talk a little bit about the basics. So the crystal is basically this resonator, this frequency selective element that we just talked about. And in the quartz crystal, that has to be bolted to some oscillator circuit that's usually integrated into the ASIC microcontroller FPGA. And that has the sustaining amplifier that generates the gain around the loop and also generates the broadband noise for startup and enables it to generate a clock signal. An oscillator basically integrates this sustaining amplifier inside the package, so you have a complete package device, and it generates the output clock to the input of the device. Basically, this is integrating the resonator and the oscillator element. This has been classically the SiTime market, and we've expanded since we into clock generators and jitter cleaners and so forth. But this is kind of how SiTime started with the XOs, crystal oscillators. And of course, we've also added temperature compensation for TCXOs and more recently ovenization to deliver 5 ppb OCXOs. But this is basically the core of what SiTime has offered. And then more recently, we have the clock generators and jitter cleaners. So what are MEMS? So, we've been talking about resonators in general. In the past, it's been Quartz is the resonant element, and now we're in the era of micro electromechanical systems. That's basically what the acronym MEMS means, micro electromechanical systems. And these are tiny machines that in some cases physically move, and they're built using semiconductor processing techniques. And actually, MEMS in this form has actually existed since the 1960s, is when this lithography techniques to make these little micro machines first started. The first mass commercial deployment was really in the early 90s. There were two companies that really deployed these, not for clocks, but for gyros and accelerometers. One was Analog Devices with the airbag actuators, and the other one was Texas Instruments with the digital micro mirrors for the DLP projectors. So this technology has been in mass production, this fundamental MEMS technology, since the early 90s in terms of billions shipped. And to date, SiTime is shipped almost 2 billion, just our company. So this is kind of the point of this is a very stable and pretty much, I would say, mature technology now. A few years ago, SiTime oscillators, MEMS oscillators were kind of considered new and so forth, but that's not true anymore. This is a widely accepted technology. As Vince mentioned, we have, I think, close to 10,000 customers in all different kinds of applications. So this technology has really been embraced by the market, and it's also kind of that embracement of our technology is also kind of reflected in our revenue growth and our stock price. So I would say that we're at the point now where MEMS oscillators is mature technology. So now I'm going to talk a little bit about how our version of MEMS resonators work. Now there's two main types of resonators. Ours is called the electrostatic type of MEMS, and the other one is piezoelectric, which is similar in function to how Quartz works. So in the electrostatic MEMS, basically you have these basically two electrodes, the drive and sense electrode, and then you have your bias voltage, which generates a voltage on the center electrode. So you have your bias DC, and then you have your drive voltage. And if you basically combine those, you get this signal that's going into the drive side of the resonator. So you can see this DC bias voltage and this this AC signal that swings around the DC bias. And what this does is this this AC voltage basically exerts a force on these electrodes, and this force pulls this center beam with the DC bias towards the drive electrode and then away from the drive electrode as you go above and below the bias voltage. And this movement across this gap generates a changing capacitance. And so basically you generate this resonance where the resonant frequency is proportional to the stiffness quantified as Young's modulus over the mass, and you take the square root of that. And it moves back and forth. And then on the sense side, this changing capacitance, basically what that does is it induces a current on the sense side, which is measured. And that's basically how the device works. And of course, the resonant frequency is going to be tuned, or basically the resonant frequency that's set by the construction of the MEMS is going to be the resonant frequency of the oscillator circuit. So that's how the electrostatic MEMS works. And so now we'll talk about some of the construction. And this is kind of some of the really important ways we distinguish ourselves versus Quartz is really in the construction. And I'm not going to go through all the steps, but I'm going to focus on kind of the end product. So what you have is you have a polysilicon encapsulation, which creates a hermetic seal to this silicon resonator. So the beam and the electrodes sit basically inside this hermetically sealed polysilicon encapsulation. And the key takeaway of this is the only materials in this cavity are really silicon, and that's it. The vacuum level is very high, on the order of 10 microbars. So there's, the contamination levels in here are controlled down to the ppb level. So really, it's just silicon along with the vacuum and any kind of, very, very tiny, less than 10 microbar partial gas pressures that are inside this resonator, which is very important in terms of the cleanliness level, no contaminants, and that has a positive impact on the aging and quality, which I'll talk about. Now, if we take a closer look at the cross section of an actual resonator, this is the resonator itself. This is the element that resonates, and this is the episeal, which is polysilicon. This is single crystal silicon. The resonator itself is single crystal silicon, and the encapsulation is poly, and that's what creates the hermetic seal. And before we do the hermetic seal, we go through a bake step at 1100 degrees C. And what this baking step does two things. Any kind of etch chemicals that were used to etch out this tall structure are vented out through these vent holes. So these vent holes are on average about 0.25 micron across. They allow any kind of contamination to escape, and they're sized small enough to also prevent contaminants from coming in. And that enables this ultra clean structure, which confers the very high reliability, low defect part per million, as well as the low aging. Now, this 1100 degree step has another benefit, is it anneals this. So basically, it's a stress relaxation of this structure, which is another reason for the low aging. No contaminants, are very, very trace part per billion level of contaminants. And we have this annealing step, which anneals the silicon. And the tensile strength of single crystal silicon is actually pretty amazing. It's about 7,000 megapascals, which is 14 times that of titanium, which is not a well-known fact. There's no fatigue mechanism, unlike titanium, which has a finite fatigue limit. There's no fatigue limit for silicon, so it will just continue resonating with no fatigue, no failure mechanisms. And the other thing is it kind of goes with the stress relaxation, but it reforms these surfaces, so it eliminates kind of the 90-degree corners, and it just has that stress relaxation annealing effect. So that's how our resonators are constructed. And we basically have three types of resonators. This is an exaggerated view of showing how they move. Our first generation was a 5 megahertz resonator. This is in some of our older products, circa 2006 to 2008. Our newest megahertz products use the 48 megahertz resonator, and our TCXOs actually use two of these, one as the reference for the PLL and the other as a temp sensor. And then our kilohertz products use this 524 kilohertz resonator. And of course, we divide down to generate the 32.768 real-time clock frequency. So how do we make MEMS oscillator? Basically, it's similar in principle to Quartz. We take the MEMS resonator instead of Quartz and bolt it up to a sustaining amplifier, and then we make an oscillator. And of course, we have squaring buffers and so forth to convert this sine wave to a square wave to the output. But it's the same principle. We just use a MEMS instead of a Quartz resonator. So now we'll talk a little bit about more what's inside the CMOS IC. So I'd mentioned that we have a MEMS resonator, and then we have our CMOS IC with the sustaining amplifier. Besides the sustaining amplifier, we also have a fractional PLL, and bolted to this fractional PLL is a temperature sensor with temperature compensation logic. We also have a non-volatile memory, so we can factory program the PLL dividers to generate a specific output frequency, and it's done that way instead of cutting a different MEMS resonator for a different frequency. And that gives us tremendous flexibility in terms of stocking blanks, field programmable blanks, so to speak, that are programmed to order, as opposed to if a non-standard frequency comes up in the Quartz world, they have to cut a different Quartz frequency and deliver that to the market. So you're looking at potentially 16-week lead times or higher. If a new frequency comes up, which is in the frequency range of a given family, that's just a PLL programming exercise that can be done by SiTime, of course, as well as our channel partners have some field programmers that can program the output frequency. So lead time has been historically a key advantage for us because of this PLL approach. So the MEMS resonator, it does have a frequency versus a temperature characteristic, and that goes into the fractional PLL. But we basically sense the temperature of the CMOS IC, we feed that into our temperature compensation logic, and then we apply the inverse of the known frequency versus temperature curve of the MEMS resonator, and we generate the output clock. And so we generate a relative stable output frequency with the temperature compensation. And one other thing I'll point out is all of our products are temperature compensated, even our so-called XOs. It's just they're not temperature compensated to the same extent as a TCXO or a OCXO. And the other thing that we have is we have multiple voltage regulators on some of our devices. One of our TCXO devices has 14 different voltage regulators, the different blocks, the phase frequency detector, band gap, of course, the output and so forth, to really, that gives us an advantage in terms of power supply noise rejection. So that's what the part looks like. So actually, it's quite a bit more complex because of the PLL than a comparable Quartz. But that PLL gives us an enormous amount of frequency flexibility and programmability, which is the benefit of the PLL. And this is how we build our products. So basically, it's usually a stacked configuration where we have the CMOS IC on the bottom. We have the MEMS resonator on top that's either bond wired. Our latest MEMS resonator actually is a small little chip scale package, which just bonds down to the pads that sit on the CMOS IC, and that's an even better electrical, lower inductance connection. And this is just a scanning electron microscope showing how the bonding is done. And basically the tiny size of the MEMS die, which is on the order of 0.4 millimeter by 0.4 millimeter, allows us to get into these very, very small packages, which Quartz can't really do. So our smallest current package is a small 1.5 by 0.8 millimeter package, and it's chip scale. So we attach the balls to the actual CMOS die, and then the MEMS is flipped and then attached to the bottom of the device. And that's our 1.5 by 0.8 millimeter package. We also support the SOT23. Some of the automotive and military customers prefer the SOT23 because of these large leads, which give very strong adhesion to the board, as well as give you the inspection, easy visual inspection of the solder joint. So now we're going to talk a little bit about how Quartz does it, and then kind of compare and contrast versus what we just talked about with MEMS. So in the Quartz world, instead of silicon, you have this quartz, which is cut to different frequencies depending on the output frequency that you need, and that's your resonant element. And you have a couple different packages. You have the through-hole package, and then you have the surface mount package construction, where you basically put the resonator down inside the package. Now we'll talk a little bit more detail about this. And Quartz oscillators use custom packaging. They use ceramic typically. And the way the process starts is you attach the metal to the underlying quartz, and you attach the metal electrode. And then at this point, oscillator is within about 1,000 ppm at this step, where you apply the metallization to the underlying quartz resonator material. And then you basically attach it to the substrate with a silicone-based adhesive, I should say. And then you basically attach it to the package, and then you complete it. Couple different things to point out is this metallization is usually with silver, and silver has a tendency to corrode. So it's very important to put an inert gas blanket in here to prevent corrosion. Any kind of corrosion on this metal electrode is going to add mass, which is an aging factor. And so sealing with an inert gas is a must. You also have these different adhesives inside the package. You have your silicone-based adhesive here, and then you have, if it's an oscillator, you have an oscillator sustaining amplifier IC down here, and it's got a different kind of epoxy here. So if you think about it, inside the cavity, there's a lot of stuff going on, which I'll talk about. And these are contamination sources, which can lead to reliability and aging issues. If you compare this to SiTime, this resonator is constructed in a wafer fab that has very good contamination control, HEPA filters, and so forth. Very, very low contamination. Everything is done at a wafer scale instead of at an individual device level. And we use standard plastic packaging, standard lead frames, and so forth, except for our TCXO, which is in ceramic. So the SiTime process is, in essence, it's a semiconductor process versus, this process was developed in World War II and, of course, refined over the 7 decades since then, but it's fundamentally the same process. It's just been tweaked and refined. Whereas I kind of can say this is a 20th century process, and then the MEMS with modern lithography and semiconductor processing techniques is a 21st century process. So this we kind of talked about already. So this is kind of the complete high-level 23 steps of building a quartz oscillator. And I kind of talked about these steps already, but the other key I want to point out and underscore a little bit more is these 4 steps here are done with an open cavity. So you attach the CMOS IC that is your sustaining amplifier with this glue that you can see down here. You attach the bond wires, then you mount the crystal resonator over top, kind of like a diving board over a swimming pool, with a different kind of adhesive. This is silicone-based adhesive. And then as a final step, remember I said that kind of at this point, it's within 1,000 ppm. To fine tune this to within 50 ppm, 25 ppm, if it's a TCXO, it's sub 1 ppm. You fire an ion beam in an ablative process to etch away the metal and reduce the mass until you get it on frequency. The other way is with a sputtering process to add metal. But in any case, you have the potential for metal fragments from either adding or subtracting metal to fine tune that frequency on the order of a few ppm or less than a ppm. And all of those are contamination potential. If they later, after the package is sealed, if those metal particles migrate to the surface of the quartz resonator, it will add mass and reduce frequency, and that's an aging mechanism. And then the final step is a high stress step. So they have to weld the Kovar lid on top of the package to seal it. And that's a high stress event. So you can have residual stresses inside the package. A lot of the companies do have a bake process at the end, but that's a high amount of residual stress and you think about the bake temperature is 125 degrees to anneal out these residual stresses. That's nothing compared to the 1100 degree bake step that we do for the MEMS resonator. So by contrast, we use standard semiconductor processes. We have a lead frame, we attach the CMOS IC, we mount the MEMS resonator on top, we attach the bond wires, we encapsulate in plastic, and then we're off to the races. And as I'd mentioned, within a given product family, it's the same MEMS resonator frequency, same design, and we generate the different output frequencies with the PLL. We don't have to go back to the beginning of the process and cut a different frequency of quartz. So what does all that mean? I mean, what does that matter in the real world? Well, how it matters is really with much, much higher reliability. So our latest mean time between failure is about 1.96 billion hours mean time between failure. Quartz, on the other hand, you're typically going to see tens of millions of hours. We actually pulled data on 2 of them that had public data anyway, and you can see that there's about a 50x better reliability expressed in terms of mean time between failure. And then you can see if you extrapolate that out to failures per year per 10,000 units, you can kind of see the scale difference between SiTime and Quartz. So now we'll talk about some other benefits of SiTime products. And these are kind of the topics we're going to talk about. You saw the shock resilience in the video, but I'll actually show some data. We'll talk about vibration sensitivity, extreme temperatures, aging, power supply noise, etc. And I've kind of already touched on quality and reliability, but we'll talk about that a little bit more. So one of the key advantages of Quartz is the low acceleration sensitivity. And the reason for that low acceleration sensitivity is the low mass of the resonator. So a SiTime's MEMS, because of its tiny size compared to Quartz, is lower mass than Quartz, on the order of 1/1000th to 1/3000th. So, you know, with the simple force equals mass times acceleration, you can see that there's a 1,000 to 3,000x scale difference in terms of acceleration sensitivity compared to Quartz. So we decided to put our parts on a shaker and measure phase noise and under vibration. So in this case, we're using a random vibration profile from 15 hertz to 2 kilohertz. And this is the phase noise under vibration of the SiTime device versus Quartz. And you can see just from the plot that you don't even need to read this bullet down here. You can kind of see from the graph the vibration range from 15 hertz up to 2 kilohertz because the Quartz responds to that vibration with about a 20 dB or so, 10 to 20 dB increase in phase noise, which obviously has an effect on system performance. And so that's basically phase noise under vibration. And then if we look at, so this is kind of random from 15 hertz to 2 kilohertz. We can also do sinusoidal vibration at a single frequency and measure it and then sweep that single frequency. And so we compared some of the good Quartz oscillators out there compared to our latest Super TCXO, which is in 5 by 3.2 millimeter ceramic. And you can see the scale difference in terms of vibration sensitivity and parts per billion, frequency shift per G of acceleration. Standard Quartz is going to be on the order of 1 to 10. Your best vibration hardened Quartz is going to be, the best I've seen anyway, is about 0.1. And then you can see with this Super TCXO, we're even an order of magnitude better than that. Typically, what we see in a given direction is about 0.004 parts per billion per G. And then if you do a gamma vector, the square root of x squared plus y squared plus z squared, we're going to be on the order of 0.009 parts per billion per G of acceleration. So you can just see the huge scale difference between the vibration sensitivity of Quartz and SiTime, and it really has to do with the lower mass of our resonator as compared to Quartz. So this is some more detailed data. In this case, we looked at, I think it was 30 devices or so, and we looked at these at the different vibration frequencies from 15 hertz up to the 2 kilohertz. This is the 6 ppb per G line right here, so you can see the highest the most sensitive device was a little bit less than 0.006 ppb per G. Total gamma, that's the square root of x squared plus y squared plus z squared. And then with sigma, that's how we get our 0.009 ppb per G, or 9 parts per trillion G spec in our data sheet. Then in terms of shock, we took one of our devices. This is on what we call Encore, or SIT8208, and we measured the frequency deviation under shock. In this case, this was 500 G shock, and you can see the scale difference of this device versus the Quartz devices. And then if you look at data sheets, so this is an excerpt from a SiTime qualification report versus our Quartz counterpart. And you can see the scale difference that we have in terms of our peak mechanical shock. Typically, you'll see 1500 G peak G acceleration from shock. And then we measured 30,000 G. So we went way above that. 30,000 G, just to give you a reference point, is what you might see coming out of a tank barrel, shooting a projectile out of a tank. So our latest Mil-Aero parts are actually rated for 30,000 G peak acceleration, and they're being used in munitions, and as well as our kilohertz products. And then you can see also the scale difference in the vibration, the constant acceleration, 20 G peak versus a 70 G peak. So airflow, you saw that really in the video with the fan. But if we basically take Allen deviation data at different averaging times and then compare that to Quartz and still air versus airflow inside an oven, you can see that under airflow, there's very, very little, almost no impairment of the Quartz. But you can see that, or of the MEMS, I should say, compared to the Quartz. By contrast, the Quartz, particularly at low averaging times, has a increase of about 38x versus the still air condition. And again, this is comparing to the Raycon Pluto RPT 7050P. And you can also quantify, we're looking here at short-term frequency stability. You can also look at wander generation. So this is a synchronous Ethernet spec, basically the wander generation spec. And this shows the maximum time interval error versus the spec. And you can see the huge margin that we have. This is showing our OCXO versus the new synchronous Ethernet, 5G synchronous Ethernet, the G.8262.1. So we have 50x margin to the latest synchronous Ethernet spec for 5G. Extreme temperatures. We showed in the video kind of what happens under a fast temperature ramp, but our temperature compensation hangs in there even with extreme temperatures. So this shows the frequency stability of our TCXO, which has a data sheet spec of -40 to 105 degrees C. But we kind of went way outside of the spec and went to -60 up to 125. And of course, we don't guarantee the device across these ranges. But what this shows is the device, doesn't go haywire like some Quartz devices do when you go beyond the rated temperature, because of very, very robust temperature compensation. And our latest TCXO, which is what this is showing, we have a 7th order polynomial temperature compensation, and that gives us a very good performance. So even at these -60 to 125, we meet our 100 ppb spec. Of course, we don't guarantee it, but if you take some typical devices, it will hang in there. And this shows basically our TCXO versus OCXO when you go above the rated temperature of 85 degrees C. This shows several of our TCXOs up here versus the OCXOs. Basically, when you go above the OCXO oven temperature, it's not going to be able to maintain regulation, and you'll see a pretty significant degradation in frequency stability for OCXOs. And
Hey,
another,
hey, Jim,
yeah,
real quick, there were a couple of questions on the chat.
uh-huh.
One was, how does MEMS compare with phase noise? How does MEMS compare to Quartz with phase noise? And then also, what about super high shocks? I think there's one in there. Well, 10,000 Gs, I don't think it's an issue, but 100,000 Gs. You want to talk about that?
Yeah, so I'll talk a little bit about phase noise. And
Okay.
so phase noise with the PLL, we're going to basically have, let me go back to this slide. So this shows our TCXO under vibration. So you can see close to carrier, we're going to be comparable to Quartz and maybe even better than Quartz. In terms of the phase noise, like between several kilohertz up to 100 kilohertz, depending on the Quartz device, we may be a little bit higher due to the PLL with a little bit higher integrated phase jitter. What this is showing is our latest Elite TCXO. With our newer Atna EXO, we've lowered basically this phase noise from the far from carrier phase noise, I think 5 to 10 dB or so, dBc per hertz. So we've definitely improved our phase noise kind of in this mid band. And then we have another roadmap product called Sapphire that we should be equal or better than the best RF grade frequency control devices on the market. But there are some Quartz devices where phase noise is better, even across this mid band. So it really depends on the Quartz. Against the best Quartz, this Elite is going to be a little bit higher in this mid band. But we're addressing that with our latest product that we codename Atna, which is a differential EXO, and also with with an upcoming device called Sapphire, which is RF grade TCXO. On the super high shock, we've done survivability tests up to 30,000 G, as you saw on the slide. We're looking at going even higher than that, 30,000 to 50,000 G. And actually, we have a plan to get in the lab in the next couple of weeks to look at 20,000 G performance, which means it's not just survivability, but we've got a frequency counter mounted to the device, and we can see how much the frequency moves during the 20,000 G shock. And then kind of more longer term, there is a lab in Cleveland that can support up to 100,000 G, and we may look at doing that either towards the end of this year or early next year. But that's a good question. We do have plans to look at higher than 30,000 G shock, and we have one particular Mil-Aero customer who's going to help us do that with their shock facilities. This is a company that makes laser guided bombs and tank shells, and they're very interested in this as well, and they're willing to help us. But yeah, both good questions. Thank you.
Hey, Jim, there are two
Yeah.
more questions. One is on radiation tolerance. So you want to talk about the radiation testing that we've done, and then the operating frequency range of the MEMS. And we have quite a spectrum of products there covering the frequency range. So you should probably talk about that as well. And then the last one is power consumption comparisons and plans for reduction.
Yeah, so on operating frequency range, our oscillators with the latest differential EXO that we have go up to 1 gigahertz. And then with our clock generator that we have, it's an 8 to 11 output, depending on which particular family member you pick. It can go up to about 2.1 gigahertz. And so, yeah, I would say, we span the frequency range of 1 hertz. We can actually program, our kilohertz products down to 1 hertz. And at the high end, I would say 2.1 gig with our clock generator and jitter cleaners. In terms of power consumption, our standard vanilla flavored exos, kind of our workhorse exos, like the SIT 1602 and so forth, are going to be on the order of, you can see it here, 3.1 to 4.9 milliamps, depending on the frequency. And we do have very, very low power offerings in this kilohertz side in our mobile and IoT, where we go down into single digit microamp for a 32.768 kilohertz product. We do have the SIT 8021, which is optimized as a low power megahertz product. And it can go from 1 megahertz up to 26 megahertz, and it goes from about 60 microamps up to 280 microamps. So we kind of span the range. The higher performance products with better phase noise are going to be higher power, on the order of, like our latest TCXOs, on the order of about 40 milliamps or so. But we do have low power products. If jitter and phase noise is not a key concern, we can go down to 280 microamps up to 26 megahertz. And was there another question that I missed in that?
Yeah, it was on the radiation. Just want to describe the radiation testing that we did on the military parts.
Yeah. So that's a good question. So we have this Mil-Aero product line that we did extra Mil-PRF 55310 testing, as well as radiation testing. And so what we found, and it really was kind of what we expected, is our parts are not radiation hard, but they do have some radiation tolerance. So these TCXOs, for example, in terms of total ionizing dose, passed up to 10.4 K rad. And we also did the neutron displacement damage dose, DDD, up to 2e to the 12th. We got a passing level up to there. And on unbiased or unpowered TID, the device is powered off. You hit it with the cobalt 60 gammas. We got up to 100 K rad passing, but powered or under the bias condition, it was 10.4 K rad. And on some of our like standard oscillator products that are within this Mil-Aero umbrella, like the 8944 and 8945, passed up to a little bit over 20 K rad total ionizing dose. And the neutron was a 2e to the 12th, just like the TCXO. We have done single event effects. We may do that. That gets asked a lot, but we have not done single event effects yet, like single event upset or latch up. Any other questions? So I think we're kind of right on time. I do have some other benefits here, and I'm glad we made time for your questions, because that's really important. This is the frequency versus temperature slope, which is important for TCXOs. Basically, it's a measure of the temperature sensitivity of the device, measured in ppb per degree C. And you can see we're much better than Quartz across the temperature range due to our superior temperature compensation. You actually saw that in the video. You hit us with a hot air gun, we don't move. And if you basically take the frequency versus temperature, the derivative of that plot, you get your dFdt, delta F delta T, and we're much better in that regard. Power supply noise rejection, this is for our differential products. You can see that we're 3 times better than the next Quartz that we looked at, and that's due to all the on-chip regulators that we have to filter the noise coming into the power supply. The aging, so this is the aging of our TCXO, and there are a couple things I want to point out here. We measure our aging at 85 degrees C, which is worst case. Aging accelerates at higher temperature. A lot of our Quartz competitors only specify in the data sheet 25 C. We specify 85 degrees C aging. And even with kind of 25 C versus 85 C, we're 8x better. Our TCXO has an extrapolated 20-year aging of about 0.4 part per million. And Quartz is going to be 8 to 10 times higher than that. A typical Quartz 20-year spec for a TCXO will be plus or minus 4.6 or plus or minus 4. So you can see kind of the 10x scale difference. And that aging goes back to the construction. Remember how I talked about, the vacuum, 10 microbars of vacuum, nothing in there except silicon, and versus the Quartz, which has the two glue types, potential metal residuals from the fine tuning of the crystal from either ablation or sputtering, adding metal, and so forth. And besides the better quality and reliability, that also confers much, much better aging specifications. Another thing that we're have an advantage is electromagnetic susceptibility. So this is where we're the victim and we're basically hitting our device with an electromagnetic field. And we've seen about 35 dB lower. The reason for that is the very, very low, the short bond wires that connect the MEMS resonator to the CMOS IC. And basically that's a very, very short antenna, shorter than typical Quartz construction. And so our susceptibility is typically much lower. We had one tractor vendor in the mid-Northwest that were comparing a Quartz, they used a Quartz crystal historically, and when they did the lightning test, energizing the chassis to 30,000 volts, when they had the Quartz crystal, the CPU went into reset because of the transient on the interface between the Quartz crystal and the MCU. And they put our oscillator in, and there was no problems at all. And the reason is for that short bond wire connection. And of course, the logical question is, well, this tractor company has been doing this stuff for, probably 100 years, or at least in the electrical world, maybe 50 to 60 years. What was the difference? Well, the difference was they decided to go from metal to plastic enclosures where they could get away with it for lower cost, lower weight. And by going to plastic, they lost their Faraday shielding. And without that Faraday shield, the Quartz crystal just couldn't hang in to that very large field that got induced by the emulated lightning strike. And then we talked about quality and reliability. I touched on that kind of after we talked about the process, and you've already seen this one. And then this is our portfolio. So basically, you've kind of seen this as I went through some of the other testing that we've done, but we have our mobile and IoT. This is our low power kilohertz products, the frequency span is from 1 hertz up to 26 megahertz for these low power devices. Then we have our industrial and consumer, automotive, communication and enterprise, and then the mil-aero. And then within this communication and enterprise is where our new clock generators and jitter cleaners are located. And you can see we offer from 8 output up to 11 output devices, 4 inputs. These are very, very flexible devices. You can basically build a clock tree with one device. And as long as you need 11 or fewer clock outputs.
Hey, Jim, we got a couple other questions here. Let me go in reverse order because I think it's easier this way. Do we use analog devices chips for phase lock loop? And the answer is no. We've got the built-in phase lock loop on all of our oscillator products and on our clock products, multiple output clock products. So no, we don't use ADI chips in our technology. The next one, Jim, is on programming the output frequency, and it says end customers program the output frequency, and the answer is that with our Time Machine 2 programming kit, which is available in distribution, customers can purchase that kit and they get a number of different blanks, or we can provide a number of different blanks. They can use that kit to do prototyping programming. Our chips are one-time programmable. They cannot be reprogrammed, but these TM2 kits enable engineers to do programming in the lab. There's a programming disk in that kit. There's a cable that goes from that disk to an engineer's laptop. There are a number of different sockets to accommodate the different packages. And there's a nice graphical user interface that comes up on the screen that enables customers to do prototyping programming. Other than that, we do have a device which is the 3521 family, which I think is shown on here as well, where a customer can either set a center frequency and using that the SPI port or the I2C port, pull the frequency up or down, or it can set two frequencies and then use that port to toggle between the two. So that's really the only customer programming capability that we offer. Other than that, the technology is one-time programmable. And then the last question, Jim, is for the total immersion dose, is the 10.4 kRad limit due to the MEMS or CMOS or both?
CMOS. Yeah, the failure was on the CMOS IC when we measured above 10.4 kRad. So we don't think the MEMS is going to be susceptible to that at all because it's a large structure. It's a mechanical resonator. So it was the CMOS IC which was the weak point during the total ionizing dose radiation testing.
Well, folks, thank you very much. This is Rick Sapp.
Jim, wait a minute, Rick. There's one more question. It has to do with hermeticity. It says, are the devices hermetic? Is it true for all of our devices or a subset? And can you explain?
Yeah, so our devices, so this, let me go back to this construction slide that shows it. So we do have a hermetic seal between at the MEMS resonator level. So they are hermetically sealed. And then with the latest TCXO, we have an extra ceramic hermetic enclosure around it. So yes, they are hermetically sealed.
And then one more question about unloaded Q of the 48 megahertz resonator. It says it must be on par with that of a crystal since the close-in phase noise is the same.
Well, actually, yeah, the close-in phase noise, it depends on the crystal, but our close-in phase noise can actually be better than Quartz. The unloaded Q of that 48 megahertz is about 150,000. And typically Quartz is going to range from 10,000 up to 100. So just depending on the Quartz blank and how the quality level that it's constructed, we're going to be better typically.
Well, that's it. Go ahead, Rick.
No, I was just going to say thank you for everyone for participating, and Vince, you and Jim for presenting. I'm assuming you guys will stay on for as long as if anybody's got any more questions they want to ask or go through chat. But those of you that need to jump off, thanks very much again, and we'll sit tight for a couple minutes to see if you have questions, and then we'll let go.
Okay, here's another one. What is the maximum analog pullability of our VC TCXO?
So actually, that raises a good question because we don't pull in an analog way. Typically, a Quartz VC TCXO will basically pull the resonator with voltage-controlled capacitors called varactor diodes. And so your pull range is limited by how much you can pull the resonator. Our pulling action is through the fractional feedback divider, so there's no limit in that regard. And our current VCXOs have a pullability of about, that can be programmed or user selected from plus or minus 6.25 ppm all the way actually up to plus or minus 3,200 ppm. Yeah, very good questions.
So the question is it pulled in steps?
Yeah, so the resolution of the pull, it's a 26-bit fractional feedback divider, so the resolution up to 200 ppm is about 5 parts per trillion, which is pretty low. So that's usually, you can't even see that, to the outside world it looks analog, but it's 5 parts per trillion frequency resolution.
Okay, then we have a question about thermal hysteresis. Can you talk about thermal hysteresis for your best performing products and any plans to reduce further?
Well, yeah, I mean, the thermal hysteresis is included in our overall frequency versus temperature stability spec. And so, whatever that spec is, like for our TCXO, our best spec is plus or minus 0.1 ppm from minus 40 to 105 C. So the hysteresis will be, a subset of that. It'll be smaller than that. I want to say that we've observed very, very low hysteresis. I don't have a slide for that, but I want to say it's on the order of maybe a third of that budget, maybe 30 parts per billion or so. I want to say, but we do have some hysteresis plots that we can share.
Okay, well,
Any other questions? Okay. Oh, wait a minute. Oh, great job.
Thanks, Scott.
so yes, thanks again for all those that participated, and thanks again, Vince, to you and Jim for doing a great job of presenting. And if those that are left on the line, if you have any other questions at all, please feel free to reach out to your to the local megahertz rep in your territory. So have a great day. Thanks again. Bye now.
Yeah. Thanks, everybody.
Thank you. Bye-bye.
Bye.